Okay, hello everybody, and welcome to our second session of Beginner Track++ workshop. Today we are going to be covering Introduction to Graph Theory. So here is the link to the slides, so feel free to follow. But before we start, last week we had a contest and we ran a raffle, and now we have a winner. So the winner is Pawan Kumar. Yeah, you're getting $25 gift card from Amazon. So if you are here, please send us your email. We'll contact you. Okay. Now let's get started. So today, first we'll talk about what a graph is. Then we will discuss how to implement it. We'll cover most popular traversal algorithms, BFS and DFS, and look into some example problems. And finally, we will have a contest where you will get a chance to win another $25 Amazon gift card. And something new we are starting this quarter is that if by the end of the first part of the lecture, you don't feel ready for the contest just yet, we'll have more example problems, so you can stay in the main session and work through the problems with us. Okay, now let's get started. So, does anybody know what a 6 handshakes rule is? So for those who don't know, this is basically the theory that claims that we can get to know almost anyone by connecting just through 6 people or even fewer. So I was thinking if it's really true. So let's imagine we decided to check that among people in our friendship circle. So to do that, we traced all these connections. So we know that you are friends with Alvin, Bill, and Lenny. Alvin is friends with Bill, Emma, Farn, Giovanni, and you, and so on. This list is great, but it's also could be difficult to see connections. Represented this way as a list, there isn't any immediate way to easily see how many connections are between any two contacts. So let's make it more visual. So let's represent people as dots and connections as lines. So we know that you're friends with Alvin, Bill, and Lenny, so we connect those dots. We also know that Alvin is friends with Bill, Emma, Giovanni, and Farah. And knowing the rest of the list, we can fill it in. Now, it's a lot easier to trace these connections. And for example, as you can see, now we can see that 6 handshakes rule is not true, at least for these people, because to get from Wilson to Giovanni, we need to get to Rishi, then these 3 guys, Emma, Alvin, and Giovanni. So that's at least 7 connections. It's easy when there are few people in the list. And what if you are going to, what if you wanted to check 6 handshakes rule for millions of people, billions of people? How do we find the shortest path between any 2 people then? Well, by the end of this lecture, you will know that. Okay, before we get into the algorithms, let's theoretically define what a graph is. So basically, a graph is a set of vertices and edges representing relationships between objects. So for example, here you see 2 vertices connected by an edge. By the way, we can also call vertex a node. Here, to be consistent, I will always call it a vertex. Some more terminology. If 2 vertices are connected by an edge, we call them adjacent. And each vertex has a degree, which represents how many edges it has. So for example, this vertex has a degree of 3 because it has 3 edges. Okay, how do we get a graph in competitive programming? Well, to represent a graph, we need a list of all its vertices and a list of all edges it has. In competitive programming, you'll usually be given an input something that looks something like this. So basically, you're given a set of pairs of vertices that are connected by an edge. Well, you should know that it won't always be this way. And you will actually see some problems of the contest that you will need to figure out how to represent a graph differently. So some examples of graphs. Well, as we saw earlier, we can have a social network graph like this one on the left here, where vertices represent people and edges represent friendships. Two people who are adjacent to each other would be friends. Also, we can represent a neighborhood graph as one on the right, and where vertices represent landmarks and edges represent roads between them. All right, some more examples. So this is a requisite structure for computer science majors at UCLA. And now, and actually knowing how to navigate and work with such a graph could be really useful in real life. Okay, but before we get into algorithms, again, some more terminology. Well, what is a path? Well, it's exactly what you would think it is. It's just a collection of vertices so that every two neighboring vertices are connected by an edge. So here A, C1, C2, C3, C4, and B is a path. Well, cycle is a special case of the path where the ending vertex is the same as the starting vertex. Well, essentially, it's exactly what you would assume a cycle is. There is a special kind of graphs which can represent more complex relationships between vertices. It's called a directed graph. So in this case, we use arrow instead of an edge to indicate a direction. So for example, here you can see that this one vertex is related to this vertex in a way that another vertex is not related to this vertex, because we have a direction now. Having the directed graphs also means that we have a little bit slightly different terminology for those. So we define 2 degrees, in degree and out degree for a vertex. So essentially, in degree is the number of edges that are pointing to a given vertex, and out degree is how many edges are pointing away from a given vertex. For example, for this one, only one edge is pointing towards it. So its in degree is 1, and 2 edges are pointing from it. So its out degree is 2. Okay, having directed and indirected graph still cannot represent all relationships between vertices. So there is another special type of the graph called weighted graph. So what is weighted graph? Here, each edge is also assigned a weight. And by the way, they can be directed and indirected as well. An example of a weighted graph could be something like this. So let's say you're an Instagram travel blogger and you need to travel around the world. And of course, you want the cheapest way to get to every city. So this is how your flight map might look like, where the edge represents the flight connection between 2 cities and the number represents the flight price. Okay, so now as we know generally what a graph is and what kinds of graphs we can have, let's learn how to actually implement it. Oh, by the way, does anybody have any questions for now about everything I talked before? Yeah, and also if you have a question while during the lecture, feel free to drop your questions in the chat. Yeah, we'll make sure to answer them. Okay, so let's continue. Well, there are 2 main ways to represent, to store a graph. Basically, it's an adjacency list and an adjacency matrix. So firstly, let's look into adjacency list. So the general idea is that we have a vector where each entry corresponds to a vertex in a graph. And for each such vertex, we store another vector for all of its adjacent vertices. It can be easily represented by a vector of vectors or an array of vectors. So however you want, we'll cover that later. So here is an example of adjacency list implementation. So for this graph, we see that vertex 0 is connected to vertices 1 and 2. So we store them in the corresponding entry. Vertex 1 is adjacent to vertices 0, 2, and 3. So here they are, and so on. Okay. How do we actually implement adjacency list in code? Here you can see the example implementation in C++. So, for example, this line means that vertex 0 is adjacent to vertex 1, and vertex 1 is adjacent to vertex 0. So now make sure if the graph is undirected to store each edge twice, because here you can, for example, here, as you can see, we store this connection for vertex 0 and for vertex 1. And later on, it's easy to check if vertices are adjacent. You simply need to traverse through the corresponding array. And yeah, so for example, here the result would be true. Okay. So this all was about unweighted graph. And what about a weighted graph? Well, we can also implement it using adjacency list. Weighted graphs are a little bit different because they require you to store another variable entirely, the weight. So what we want to do is to store both variables together. And we want to store both the weight and the other vertex. So how do we do this? Well, luckily enough for us, there does happen to be a data structure that stores two different pieces of data together called a pair. So some syntax of pairs in C++ to declare, so here's how you declare a pair. You can access its first and second elements. And to create a pair, there are actually two alternative ways, two ways to do that. Okay. So now, as we know how to implement this pair structure, this is how you would usually implement adjacency list in C++. So basically, you create an array of vectors, and each entry there is a pair. So, for example, this line here means that vertex 0 is connected to vertex 1 with weight 5. And the next line means that vertex 0 is connected to vertex 2 with weight 1. And now if you want, again, to check if the vertices are adjacent, and let's say you want to check if vertex 1 is adjacent to vertex 2 and the weight is less than 4, you can simply traverse through the array and again, check that condition. Okay, so a quick summary of what we just learned. So how adjacency list works. For undirected graph, make sure to store each edge twice, one in the list for each vertex. For undirected graph, it's enough to store it once, depending on the direction of the edge. And finally, for weighted graphs, we use pairs to store both weight and vertex. Okay, so this was adjacency lists. Now let's move on to adjacency metrics. So here the idea is that we basically create a matrix, a table, a vector of vectors where an entry is true or 1 if there is an edge between two vertices and 0 otherwise. So, for example, that same graph would be represented in adjacency matrix in this way. So we know that 0 is adjacent to 1. So we check row 0, column 1, and it's 1. And we know that 2 is not adjacent to 3. So we check row 2 and column 3. And we see, right, it's 0, it's false, so they're not adjacent. Something to remember is that for an undirected graph, such matrix is always symmetrical. So see how we store vertex 1, edge 1, 0, and 0, 1 twice. And for directed graphs, this might not always be the case. So some adjacency matrix code in C++, right? And so always make sure to store each edge twice. Again, I want to reiterate that because I always forget to do that, and this causes lots of bugs in the code. And to check if two vertices are adjacent, you simply check the value in the corresponding entry of the matrix. So in this case, vertices 1 and 0 are connected. Okay, what about weighted graphs? So if we alter our previous example to be a weighted graph, you can see that it is simple to reflect those changes in the matrix implementation. We can simply change ones and zeros to the respective weights of the edges by only placing them in the row of the first vertex and the column on the second vertex. So, for example, we know that vertex 1 is adjacent to vertex 0 with weight 5. So we store in row 1, column 0, number 5. Okay. So, and again, a quick summary. For undirected graphs, we need to make sure to store the edge twice. For directed graphs, the convention is that we store the head vertex in the row and tail vertex in the column. And for weighted graphs, we simply store weights instead of Boolean values. Okay. So now you might be wondering, so which one do I use? Adjacency list or adjacency matrix? Because they're both really useful. And with some practice, you will actually see there is no universal rule to determine which structure you need. With some practice, you will see that the adjacency lists are more useful for one kind of problems, and adjacency metrics are more useful for another kind of problems. Generally, adjacency lists are space efficient. So if your graph has few edges, you would want to use adjacency lists. As for the adjacency matrix, it's easy to check if two vertices are adjacent, while in adjacency list you have to iterate through the entire vector to see that. So if you don't have lots of edges, you'd probably want, and if you have lots of entries of the form to check if two edges are adjacent, you would probably want to use adjacency matrix. But again, this feeling comes with more practice. So now, do you have any questions about what I just covered? Okay, then I guess we can move on. So now that we know what graphs are and how to program them, we can get into algorithms. So the main task in many problems is to traverse a graph. So given a graph, how would we actually get around it? What do we need to do to check every vertex and make sure that we don't circle back around to the same vertices? Well, there are actually two ways to do this, called breadth first search and depth first search. So let's start with the breadth first search, or BFS. So the basic idea is that we start at some vertex and explore all its adjacent vertices, then explore all of their adjacent vertices, and so on. So basically, it looks like working our way outwards. We can see that with each iteration, we are moving one edge further from the original vertex. Okay, to better understand BFS, let's do it by hand. So we start at the start vertex. So step one, we want to append or record unvisited adjacent vertices in this log on the right here. So this is where we are really going to want to look during this example. So we can figure out the properties that we want in a data structure that would facilitate BFS. So we'll be paying special attention here. Okay, let's start. So step one, we record unvisited adjacent vertices. In this case, it's 5. We put it into the log, mark it as visited, and explore the next vertex. So the next vertex in the log is 5. So we enter vertex 5, explore its unvisited adjacent vertices. It's 2, 9, and 10. Put them all into the log and mark them as visited. So the next vertex now is vertex 2 because it's on the top of the log. So we enter vertex 2, look at its unvisited adjacent vertices. It's 3 and 6. Put them again into the log, mark them as visited, and move on to the next vertex, which is vertex 10. Which is vertex 9, but 9 does not have any other unvisited adjacent vertices. So we move on to the next one, which is vertex 10, and explore its unvisited adjacent vertices. It's 14. We put it again into the log and continue with vertex 3, which was the top one in the log for now. We explore its unvisited adjacent vertices, 4 and 7, put them into the log, and so on. So, so now as we could see, what is the order of traversal here? There are two things that we need to keep in mind. So we want to know which vertices are already visited. It's easy. We can just keep an Boolean array. We can just keep Boolean array and mark true if we already visited a vertex. And another more complicated thing is to know which vertices we need to visit next. So to understand that, let's actually look how we interacted with the log. Well, it had a really simple pattern. We put vertices in some order, let's say 2, 9, and 3, and then we visited them, and then we visit them in the same order, 2, 9, and 3. Well, luckily for us, there is a data structure that works exactly like that. Queue. So some syntax of queues in C++. To declare a queue, this is how you can declare a queue. You can add an entry to the top of the queue. You can take or return element at the front of the queue. Here's how you would remove an element from the front of the queue, and you can also check if the queue is empty. So why the queue work here? Because the first element in the queue is the last out. Okay. So Now, as we know which data structure we want to use, and as we did BFS by hand, we now starting to get an idea of how to implement BFS in code. So firstly, we need to create a queue. We mark starting vertex as visited and push it into the queue. While queue is not empty, we take the vertex at the front of the queue and check all unvisited neighbors of it, put them into the queue and mark them as visited. And repeat this third step. So this is how your C++ implementation of BFS might look like. So let's go over it again. We create a queue. We put the root or starting vertex into the front of the queue, mark it as visited. While the queue is not empty, we take the first vertex in the queue, remove it, and check all of its neighbors. If there are unvisited ones, we push them into the queue and mark visited. Yeah, and that's it. So there is, so as you can see, BFS is a really effective algorithm to explore all the possible paths in the graph and finding the shortest path from, as you will see later, it's also useful in finding the shortest path. So notice that it can be especially useful in solving some kinds of maze problems, and where you will actually need to find the shortest path from the one vertex to another. So let's see how we would actually find the shortest path in the graph using BFS. Okay, so this is an extension that we can do quickly. So the idea is that we go through all adjacent vertices of one vertex, and knowing the distance we needed to get into that vertex, we will just set that path length of unvisited vertex to the current path length +1. So why does this work? Because by the time we reach a vertex when running BFS, it must be the shortest way. It must be the first time we encounter that vertex. So it must be the shortest way to reach that vertex. So the implementation of these algorithms, this algorithm is pretty easy. We only need a simple augmentation for BFS. We need another vector that we'll call, let's say, distance, where we'll keep track of the shortest distance to each vertex in the graph from our root vertex. So, and if we are currently in vertex V and we are trying to visit adjacent vertex U for the first time, so it's unvisited, we would simply use this line in our algorithm to keep track of the distance. Yeah, and that's it. So, and note that this also works on both directed and undirected graphs. So, but that's not all that BFS can do. What if we also want to know not just how long is the shortest path is, but what the shortest path actually is? So, well, this is quite reasonable extension to the problem, and again, we only need another single vector. Let's call it parent. When we for each vertex we visit, we can also keep track of the vertex that we came from, the parent vertex. So if we visit a new vertex U from vertex V, we set parent U to V. Once we finish BFS, we can use this array to backtrack and recreate the shortest path. All right, so a quick summary of what we just did, what we just learned. BFS can help us find the shortest path in a graph from some vertex. It works on all kinds of graphs, and we can not only find the length of the path, but we can also recreate the path itself. using parent array. All right. So now, as we know how it all works in theory, let's see how to actually use BFS on a real problem. So let's say you're given a connected graph on n vertices and m edges, and you have to find the length of the shortest path from vertex 1 to all other vertices. So let's work through this example. So we are given a graph with 6 vertices and 6 edges, and then we have a list of the edges. So we know that there is an edge between 1 and 2, 1 and 3, 4 and 5, and so on. And the output we get, so for vertex, we start from vertex 1, and it's quite reasonable that to get from vertex 1 to vertex 1, we need a path of length 0. To get to vertices 2 and 3, we need to pass 1 edge. To get to vertex 4, we need 2 edges. Vertex 5, 3 edges, and vertex 6, 2 edges again. All right, so here is the solution to this problem. And for now, we just implemented BFS, and we want to know how to change it so that it outputs the needed result. So let's look through this code together. So firstly, we're reading the values. Make sure to set so something you noted, something I need to mention is that in this example, we use adjacency metrics just to show an example of its implementation. Actually, it's a matter of choice, so you can use adjacency list here as well. So first of all, we're reading the values. Make sure to, because the graph is undirected, make sure to store the edge twice. After that, we run BFS, supposedly from the first vertex. And afterwards, we want to output some kind of distance to each vertex of the array. So let's see, first let's see how the BFS works here, and then we will find out together what we need to change here to get the desired result. So as we enter BFS from here, again, we create a queue at this first vertex 0, mark it as visited, and while it's not empty, we take this first vertex, go through all its adjacent ones, its adjacent vertices. So if the in this case, we need to loop through the entire row in the matrix. And if it's not visited yet, we add it to the queue and mark it as visited. So, all right, so what do we need to do here to get the distances to each vertices? Well, first of all, we need an array, right? So we declare an array. Then we want to, so as we learned before, we want to increase the value of the path length for the corresponding vertex when we visit it from some other vertex. So the reasonable place to put it would be here. So we know that we are visiting from vertex u to vertex y to vertex I, and therefore we add 1 to the distance. So is that it? So this code also seems valid, but there is also a bug here. Does anybody see the problem here? Yeah, you can just unmute and say if you can see the problem. Okay, yeah. So actually, when we declared an array, we forgot to make sure that all its values are 0. So when we enter the first vertex, the distance to the first vertex is some kind of random value. So we need to, oh, sorry, this should be here. Sorry about that. We should set the distance to vertex 0 to 0, and then we can start BFS. All right, so do you have any questions up till now? Okay, if not, let's move on to our next algorithm, depth first search. So these two algorithms, BFS and DFS, are different traversal algorithms, and the main difference between them is that in DFS we will have a different traversal order than BFS. So in DFS we start at some vertex, explore as far as possible along some branch, and then backtrack once we cannot explore anymore. So notice that here by backtrack, I mean that we return to the, I mean that we go to the closest vertex that we can explore, and it still has unexplored neighbors adjacent to it. So yeah, for example, the traversal of this graph would look something like this. So to understand DFS better and to understand the differences between DFS and BFS, let's do it by hand again. So first we start from the start vertex. We record unvisited adjacent vertices. In this case, it's 5, put them into the log, mark as visited, and move on to the next unexplored vertex. It's 5. So it has 3 unvisited adjacent vertices, 2, 9, and 10. We put them all into the log. And now we continue along one of these 3 branches. Let's say we continue to vertex 10. It has unvisited vertex 14, which is adjacent to it. We put it into the log. And notice that the next step would be going into vertex 14, not going back to vertices 2 or 9. So, and interestingly, this vertex is also the last in our log. We will need that notion later to choose the data structure we want to use. So we visit vertex 14. It has 2 unvisited adjacent vertices, 13 and 15. We choose one of those to continue, let's say 15. And then it has adjacent vertices, vertex 11. We add it to the log and proceed to vertex 11. So, and so on. So what do we notice about how we interacted with the log this time? So this time we have an interesting pattern. We put vertices in some order. Let's say vertices 2, 9, and 3. And then visited them in the reverse order. So visited the last vertex in the log. So we put 2 and 9. We visit 9 because it's the last one. Then from 9 we get to 3, and again now 3 is the last one in the log. So we visit vertex 3, and only after that we visit vertex 2. So the implementation is quite similar. In this case, we want to use stack as our data structure, which works exactly as needed. The first element in, the first out. So here is some C++ syntax cheat sheet. So here's how we declare a stack. We can push the number into the stack, then take the number from the top of the stack, and we can delete the number from the top of the stack, and also check if the stack is empty. If you try to implement DFS using stack, you will realize that it's quite complicated, and luckily there is an easy way to do it: recursion. So for those who don't know, recursion is the process when function calls itself when we run it. So for example, if we need to calculate n factorial, and instead of looping through all numbers from 1 to n and multiplying some other variable, we can simply run this code, which will call, where the function will call itself within the code. So something we know, something to keep in mind when doing recursion is that when we call the function inside it, it performs the same actions, but on the different input. And it's actually the same in DFS. When we, for example, enter vertex 2, we get the same result. So the result of the algorithm is the same if we started at vertex 2. If you don't understand recursion quite yet, don't worry. Or if you want to learn more about it, we'll be holding 2 workshops on dynamic programming later this quarter, so don't worry. For now, just keeping this information in mind, we can implement DFS recursively with this simple code. So firstly, as we enter a new vertex, we mark it as visited, and then check all of its neighboring vertices. If there are unvisited ones, we simply run DFS starting from those vertices. Okay. So yeah, right. Quick comparison of DFS and DFS here. Any questions? Does anybody have any questions about what we just said? Okay, let's see. All right, then. If there are no questions, it's time for a short break. So now it's 6:48. I'll see you. I'll see you at 6:53. So notice that we'll need to use Cadis later in the lecture. So if you don't have a Cadis account already, please create one over the break and tell us your username using this Google form. Okay, I'll see you at 6:53. Yeah. All right, all right. Let's keep going. So now, as we learned what BFS and DFS is, what BFS and DFS are, let's learn actually some algorithms that use BFS or DFS. So one algorithm we want to start with is to check the connectedness. Let's look into this example. So what if you saw the news about UCLA going online until the end of January and quickly decided to fly back home to your city? You check the flight schedule, and here's what you saw. So can you reach your home city from where you are? No. Well, and hopefully unrealistic. This is a good example of a disconnected graph with 2 components. So what a component or connected component is. Essentially, it's a subset of vertices and edges such that there exists a path from each vertex to each other vertex. If this is true for every pair of vertices in a graph, this graph is called connected, like the one on the right. And for example, this one on the left has 2 connected components. All right, so let's say we want to figure out if a graph is connected or not. Let's see how we do actually do this. Well, determining if which components are connected is quite intuitive. We simply run BFS or DFS until we cannot do this anymore. So the idea is that if you finish running BFS or finish running DFS and you still have vertices that are unvisited, this must mean that these vertices are not adjacent to any of the ones that we have visited already. If they were, we would have visited them before. Therefore, that means that they must be a part of a separate connected component. How do we keep track of components if we would actually want to know which vertex belongs to which component? Well, we can easily replace visited vector with an integer component ID vector. So after we finish BFS or DFS each time, we simply increment the component ID and run it from the next unvisited vertex. All right, so quick recap. To implement this algorithm, we can use both DFS or BFS. It works on any kinds of graphs, directed, undirected, or weighted. And to determine which vertices are in which component, we can turn Boolean visited vector into integer component ID vector. Okay, so now as we learn this simple algorithm, let's actually try to use it in the real problem. So please, everybody, go to this link over here, join the contest, and look through the task of problem A. I'll give you 2 minutes to do that, and we will discuss the solution and implementation together. Okay, I hope you'll look through the problem. So let's discuss it. So the basic task is that you need to figure out which houses are connected to the first one by the internet. So in the example, in the problem statement, you would see that house 2 is connected to house 1, house 3 is connected to house 2, and house 4 is connected to house 3, meaning that they all can have internet. However, vertices 5 and 6 are not connected. So basically, not connected to the first one. So basically, what you want to figure out is which vertices are in the same component as the first one, and which vertices are not. So there are three things we want to implement. Is we need to construct a graph, run BFS or DFS at node 1, and keep track of the nodes we already visited. Finally, output nodes that are not visited. That would mean that they're not connected to the vertex 1. So let's actually do that. I'll stop sharing this screen and okay. So I have some sample code over here. Right. So well, first thing I want to do is to read in the input data. So I read the number of vertices and the number of edges. Then I declared my graph here. So notice I use adjacency list here in this problem. Again, it's the matter of choice. You can use adjacency metrics as well. This is just for the sake of the example. So we have our graph and we have our Boolean array of vertices. So firstly, we want to read all the vertices. So we need to read all the edges, sorry. So we have m lines to read. So each line consists of 2 numbers, and we want to add vertex b to vertex a vector and vertex a to vertex b vector. So is it right? So does anybody see the problem here? So the issue is that the way vectors and arrays work in C++. So we would actually want to use -1 here, because we declared a graph of size n, and each entry is indexed from 0, starting from 0 to n-1. So alternatively, we could keep A's and B's the way they were and add +1 here. But in this example, I will start indexing from 0. So afterwards, so now we read the graph, we run DFS from vertex 0. And finally, we want to check if the graph is connected, and if not, which vertices are not connected to vertex 1. So to check all unvisited vertices, so we need to obviously look through all the vertices in visited array. And so if there is a vertex that is not visited, was not visited during our DFS algorithm, there are 2 things we want to do. So firstly, the graph is no more connected. And secondly, we want to output this vertex. And remember to add 1 again, because when we created the graph, we subtracted 1. All right. And finally, if it was connected, we didn't output any vertices, and we output connected. Finally, we want to implement DFS. So as you'll remember, when we enter the vertex, we set visited to true. And then for each vertex in the graph A vector, we check. So if it's not yet visited, we run DFS starting from this vertex. Okay, so this is the algorithm. You can also find it on the next slide in the next slide of the presentation. All right. Although we already discussed the solution and implementation, however, I encourage you all to solve this problem using BFS as well and submit it to Cadis. It's a nice practice. Okay, let's move on to the next example problem. Again, it's problem B in the same contest, so I'll give you 2 minutes to read the problem statement, and then we will discuss the solution. All right, I hope you all had a chance to look through the problem statement. So now let's discuss what the task actually asks us to do. The key thing we want to keep track of is the sum of money owed in each component. It should be greater than 0. To keep track of that, we'll use another integer array for each person to keep track of how much money they owed to others. So generally, what we want our algorithm to do is to find all connected components in a given graph and check the sum of money in each component. If it's greater than 0, then it's possible to redistribute the money. If it's not, if the sum is negative, then it's not possible. So here is some example code to work with. There are some parts where you will need to write code on your own. You can follow this link and to find the entire code together on a Google Doc to copy to your editor or compiler. And yeah, so try to work through this code, do the to-do parts, and submit the problem to the KTS contest. So I'll give you around 10 minutes to do that. So feel free to ask any questions if you have them. All right, notice here that you might need to create another variable, this part of the solution, and pass it by reference to your DFS to check, to keep track of the sum in every single component. Okay. We'll continue in 10 minutes. Great. So I hope everybody got a chance to try solving this problem. I'll quickly go over the solution. So basically, there are 3 bits we ask you to implement. Well, the reading of the graph was essentially the same. The creation of the graph was essentially the same as in the previous problem. This part here, so basically what you're doing here is you're trying to, so if the vertex is not visited, you're trying to run DFS starting from that vertex. So if the vertex is not visited, that means that it's not in any connected components yet. So we want to run DFS starting from that vertex to recreate the connected component that includes that vertex. And while doing that, we'll keep track of the sum variable here. And afterwards, if the sum is greater than 0 in that connected components, we say that it's impossible to redistribute the money. So what changes do we need to make to our DFS algorithm? Essentially, when we receive, when we pass some variable by reference, when we visit another unvisited vertex, we add its amount owed to the sum variable and simply continue DFS. Afterwards, we'll get the sum of money owed for all vertices in that connected component. All right, so so for now, the first part, this is the end of the first part of the lecture. So around 5 minutes ago, the contest started. Something to keep in mind, starting from this week, to enter the raffle for $25 gift card, you need to fill out our feedback form as well as solve at least one of the problems on the contest. So, and more solved problems means more entries for the raffle. So make sure, we really want your feedback. Make sure to fill out our feedback form. It's really short, just several multiple choice questions. So now we are gonna have really short break, just several minutes for you to look through the contest problems. And if you still think that you are not ready for the contest right now, you can stay in the main session and we'll continue going over the example problems. But if you want to start working on the contest, I think we'll have our breakout rooms for each of the problem of the contest. You can enter those rooms, and just if you have any questions about the problems at all, one of our officers will be there to help you. So yeah, just a quick 2-minute break, and I'll see you in 2 minutes. Yeah, just try filling out, please fill out the feedback form and look through the contest problems. The contest will be open for the entire week, starting from now. So if you decide not to work on it today, you will still have time to try yourself. Okay, so please fill out feedback form. I'll see you in a couple of minutes. All right, we'll keep going now. So if you feel ready for the contest, feel free to start working on the problems. And I'll go over, and I'll go over more problems, more example problems in the main session. So please follow this link. We'll be working on this problem. I'll give you several minutes to look through the problem statement, and we'll try approaching this problem together. All right, so let's discuss what the problem actually asks us to do. So at first, you might have noticed that at the first glance, it doesn't look like a problem on graphs. And maybe something that it's like a hint that you might find helpful to see if the problem is requiring you to use graphs, is that you're given a list of pairs, some kind of vertices that represent some relationships between two elements. So this is actually what we have here. So it's really helpful in this problem to draw it out. So when we draw it all out, we get this directed graph. So for example, we can see that that R can be translated into O, which in turn can be translated into C, into T, E, and F. However, R cannot be translated into K or I because they do not have an edge or a path leading from R to K. So we are going to want to use an adjacency list representation here because there are quite a few connections. So let's see how our program will work. So generally, we are given two strings, the starting and the ending word, and we want some kind of function to check if one word can be translated into another one. So let's look more closely how the function solve could be structured. So basically, if the two words are different lengths, then of course they cannot be translated into each other. Then we want to check if each letter of string start can be translated into the corresponding letter of string end. To do that, what we want to do is to check which letters can the start I. So let's look at the letter start I, and we want to check which letters start I can be translated into. And then if end I is not among those letters, we return no. So for now, I'll leave you with this basic understanding of what you want to do, try to draw it out, and implement adjacency list based on the graph representation we've just discussed. So basically what you want to do is to run DFS from every letter in a word and run until you can and mark vertices, note down vertices that you visit. And then, for example, for R, you would mark R, O, C, T, E, and F. And if K, for example, is not among those vertices, you cannot translate a letter into another letter. So try to implement this adjacency list and function solve. I'll give you around 10 minutes to do that. And afterwards, we'll discuss the problem solution together. Right, feel free to use any code you saw in this presentation. It can be helpful. Yeah, maybe some of you noticed how we used start I minus A and I minus A here. This is because we want to represent our entire alphabet from A to Z as an array, and as an integer array from 0 to 25. So this representation can be quite useful, not just in this problem, but in all problems that require you to work with letters or words in the English alphabet. All right, it's been roughly 10 minutes. So let's go over the implementation. So the first thing we want to do is to actually create our graph using adjacency list. So this is how you would do this. So we can create an adjacency list to represent our graph of size 26. So we have an array of size 26, one for each letter. And then in each vector corresponding to an entry in array, we store another vector of letters that can be reached directly from that letter. So let's see how our DFS would work on such adjacency list. Well, let's say we start from some vertex. Let's say it's vertex O. We know that it's adjacent, so we know that it can be translated to letter C. So we enter letter C, mark it as visited, and proceed to run in DFS from letter C. It's adjacent to vertex T, so we proceed to T, mark it as visited. That means that O can be translated to T as well. And run DFS starting from T, we reach to vertex E. Vertex E does not have any other adjacent vertices, so we simply mark it as visited or reachable and proceed to the next unvisited vertex, simply going to another branch of vertex T. So we enter vertex F. It also doesn't have any other vertices adjacent to it. So this is what we got. We can translate vertex O, we can translate letter O into O, C, E, F, and T. All right. Notice how we notice that we need to pass vector array, Boolean vector array of visited vertices by reference here. The reason is that each time for every single letter, you have a different Boolean visited array that will represent the letters this letter can be translated into. So to So in your actual implementation, remember here, so you actually create a new array and pass it by reference to DFS function. You could also do this by declaring a global variable b and then setting it all to setting all values in the array to zeros before running DFS. But this approach is just easier. So yeah, this is how the entire solution would look like. So firstly, we declare all global variables. We'll declare them as global because we'll need to use them not just in the main function, but also in solve or DFS. So we declare our graph as a linked list and our functions. Then firstly, we store the array. So we read in the values and store an array as an adjacency list. Notice that here we only store the vertex. We store an edge once because the graph we built is directed graph. If it was an either undirected graph, we would still need to store each edge twice. And finally, for each pair of words, we run solve function. So what solve function does is compares the length of two words and checks if every letter of the first word can be translated to the corresponding letter of the second word. This is done by function DFS. DFS simply outputs the Boolean vector of letters that the corresponding letter can be translated into. All right, so this is all for today. If you have any questions, we will still be here for another 10 minutes. Please fill out our feedback form. We really appreciate your feedback. And try yourself in our contest to get a chance to win a $25 gift card from Amazon. The more problems you solve, the more entries you'll get for the raffle. Okay, so if anybody has any questions, feel free to ask them or drop them into the chat, and definitely try the contest.